Hello everybody, let's talk about effusion and diffusion. Alright, we talked about this in regular chemistry a little bit. Diffusion is when gases are mixed, and if I release some air freshener gas, it's going to spread throughout the room. Those molecules are going to spread out evenly. That's what diffusion is. Effusion is when a molecule or an atom of gas goes through a little tiny hole in whatever container it's in. So rate of effusion measures the speed at which the gas is transferred into the chamber. So if there's little molecules, they're going to move faster, so there's a better chance for them to get through the hole than a big molecule, which is going to move slower at the same temperature. So at a temperature, say 70 degrees, smaller molecules will be moving faster, so they have a better chance to effuse through a hole. And then they'll also diffuse faster too.
Of gaseous atoms flowing into a vacuum through a hole in a container. The rate of effusion of gas molecules at constant temperature and pressure is inversely proportional to the square root of the molar mass of the gas.
I totally agree with everything she said. And we'll look at the equation for that in a tiny bit. Now let's hear about diffusion.
Diffusion is the process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the two gases meet, a precipitation reaction occurs, forming ammonium chloride. The mass of the hydrogen chloride molecules relative to those of ammonia is greater. Thus, hydrogen chloride molecules travel more slowly.
All right, so you can see there, because the hydrogen chloride molecules, which are about 36 in mass, grams per mole, and the ammonia, which is about 17, the ammonia is able to travel faster and further before they meet. So, of course, there's got to be a formula to go along with this to try to figure out how we can compare gases and their speeds. So the rate of effusion is going to be the square root of M2, so actually the gas here, divided by the square root of M1, so the first gas you're talking about. So the M1, the big capital M, is going to represent the molar masses of those gases. I think I just rhymed. Now, some problems that we have here. Let's try a couple problems. You have them on your handout. So the first one is, what's the ratio of the effusion rates of N2 and O2 in the air? So we have our R1 over R2, you'll notice this is on your green sheet, is equal to the square root of M2 over square root of M1. Those are capital M's, of course. Now we're talking about oxygen and nitrogen, so we're going to say, what's the rate of nitrogen to oxygen? So we're taking the square root of N2, well actually O2, because these two go together, just like R2 and M2, they go together. So O2 would be 32.00 grams per mole. The N2 would be 28.02 grams per mole. So we need to take the square root of those. If I take the square root of this, it's 5.65, blah, 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 blah. If I take the square root of this, it's 5.29, blah, 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 blah. I divide those two numbers. Actually, you need 4 sig figs, so there's more here that I'm not writing. But I get 1.069 to 1. I can look at that. So the nitrogen is going to diffuse faster than the oxygen, which should make sense because it's lighter. So the lighter one is here, and the heavier one is here, the oxygen. So it should diffuse faster. The nitrogen should diffuse and effuse more than the nitrogen. So this is the rate of effusion. All right, the other problem that's on there is number 104 in your book in Chapter 5. This is on page 230. And again, we're going to use the same equation. R1 over R2 equals the square root of M2 over the square root of M1. In this case, it talks about the rate of effusion of a particular gas, but we don't know the molar mass of that gas. So for the sake of math, I am going to keep the gas that we don't know the molar mass of as M2. I've got it on top already. I don't have to try to get the M1 up on top. So that's how I think of it. The rate of that gas, according to the problem, is 24.0 milliliters per minute. That it is effusing. And if I look at the other gas that it is compared to under the same conditions, it is 47.8 milliliters per minute, and that's methane. Which methane is CH4, which has a molar mass 12 plus 4, so it's about 16.04, but essentially square root of 16 is going to be here, grams per mole. All right. If I solve for M2, so how am I doing that? I'm going to take the square root of 16.04, which is essentially 4, times 47.8, divided by 24.0. My calculator. 4 times 47.8 divided by 24. That gives me the square root of M2 equals 7.96 repeating. All right. Well, if I want to know what just M2 is, I can square it. So I'm going to square each side. So that means I would take 7.96 squared. And I get 63.5. Got 3 sig figs in these numbers. Grams per mole. That would be the mass of the molar mass of the other gas. Does that make sense? Well, the molar mass is larger than 16, and its rate of effusion is smaller than the methane gas. So that would make sense because we have a larger gas. It's going to travel slower and effuse slower. So that's it on effusion and diffusion.